In this episode, we're going to learn how to convert density problems using dimensional analysis. But I wanted to start off with an example that is a refresher from the last time that we did some conversion factors and is applied in the real world every day. So the question says, if the exchange rate between US and euros is 0.7 euros to every dollar, what is the conversion factor that allows you to convert from US dollars to euros? So remember, conversion factors are always going to be a division line, and it doesn't necessarily matter which one goes on top first because there are technically two of them. So on the top for the first one, we have this great information right here. It says that there are 0.7 euros for every dollar. So that means for each dollar. To find your other conversion factor, you simply flip the two over. So 0.7 euros and the dollar is on top. And this can be used in figuring out how many euros you have if you had, say, $49. So let's give that a shot. So if you are given $49, how much or how many euros do you have? So you have your conversion factors. That's our first step. Our second step is to write down what you know and what you don't know. So you know that you have $49 and your unknown is the amount of euros. So our plan would be to go from dollars, because that's what we are given, and we can go directly to euros. So let's try it out. You would put $49 over 1, draw our multiply sign and our division sign. Now, because dollars is on top, we must put dollars on the bottom. That means we must be using this conversion factor on the left. So we put $1 and 0.7 euros. Dollars now cancel. And when you were to put that in your calculator, you would get 70 euros. So you can see that the amount of money you have does not necessarily change. It's just been converted into a different form. So in this episode, we're really going to focus on converting between different metric units as well as applying it to density. Okay, so in this example, we want to convert between, these are called decigrams, and we want to go to grams. In your online textbook, you have a table that helps with all of those prefixes. If you need to, if you want to look those up, you're more than welcome to. But remember, I will give you this on the test. Okie doke. So first of all, we need to write down our conversion units. So if you were to look at table 3.2, deci means times 10 to the negative second. So you know that that means it must be smaller than grams. So our equalities, we would put decigrams on top and grams on the bottom for one of them, or flip it over, decigrams on the bottom, grams on top. Since deci, according to that table, means since deci means times 10 to the negative 1, that's showing you that decigrams is the smallest one, so grams gets your bigger number, or your number 1. To make up 1 gram, you're going to have a lot of decigrams. So each decigram is equal to 0.1 grams. Therefore, you must have 10 to the first decigrams, also known as 0.1 times 10, to make up 1 gram. The same can be said for the alternative. Now we can do our knowns and unknowns. So you know that you have 750 decigrams, and your unknown is how many grams. Next, we need to come up with a plan, and because it's the metric system, it is possible to go directly from decigrams to grams. No problem. All right, let's give this a shot. So, start with what you know, 750 decigrams over 1, times, now we have to pick which equality has decigrams on the bottom. That would be our second one over here. So decigrams goes on the bottom, grams goes on the top. Since grams is larger, it gets the 1. And you would need 10 to the first decigrams to make up 1 of those grams. Let's see, do decigrams cancel? Yep, you have 1 on the top and 1 on the bottom. Are you left with the unit you desire? According to your unknown, you want grams, and we are left with grams. Perfect. So you would multiply straight across and divide by all your bottom numbers, and what you would get would be 75 grams as your final answer. And again, as always, this is taking you through each and every step that we just went through, and you can find that in your PowerPoint. Now, when you use this for density, density can be used to write 2 conversion factors. And just as before, we have to figure out which conversion factor we need. So in this question, it's saying, what is the volume of a pure silver coin that has a mass of 14 grams? The density is 10.5 grams per centimeter cubed. Okay, so let's write down our equalities for density. So since we have grams per centimeters cubed, we don't have to worry too much. It's already made for us. So our equalities are 10.5 grams over 1 centimeter cubed. That 1 is always on the bottom, but since whenever you divide something by 1, it's always the same number, we typically don't write it, except when we are writing equalities. The other option is the flip side of this one. So 1 centimeter cubed over 10.5 grams. Perfect. So our second thing is to write down your knowns and unknowns. So you know the mass. You don't know the volume because it's asking you the volume. You already have your equalities, you have your knowns and unknowns, so our plan must be to go from mass to the volume using density. So let's give it a shot. So start with what you know, which would be 14 grams over 1 times, now we have to figure out which one of our conversion equalities we can use. And since grams is on top, we want to make sure we have grams on the bottom. And the only equality that fits this description is our second equality, which has 10.5 grams on the bottom and 1 centimeter cubed on top. Grams are then going to cancel because you have grams on the top as well as the bottom, and you're left with centimeters cubed. That is a form of volume. So we've made it to the place where we want to go. So you multiply straight across and you divide by the bottom, and you would get 1.33 centimeters cubed of silver. And there you go, you have your answer. So you can see how you use density as a conversion factor to determine the volume of a sample, and you can use that same dimensional analysis in multiple different situations. And as always, you can go through each and every one of these for your knowns and unknowns in that equation. It's all in your PowerPoint, including things that are crossed off. If you have questions, it helps you hopefully work through a few of them. Now, sometimes our problems aren't as easy as one step, but whenever we have those, it's a lot easier to break them down into more easily to solve steps. So when you have these complex word problems, you need to break them down into steps, and you may have to have different converting units to get through your dimensional analysis. So here we have what is the diameter of a sewing needle is, or you have the diameter of a sewing needle is 0.073 centimeters, and we need to figure out how many micrometers it is in diameter. So let's write down your knowns, your unknowns, and your equality. So first of all, your equalities that you do know, according to the table, I think it's 3.2, you have that 1 meter is equal to 100 centimeters, or the opposite, 100 centimeters per 1 meter. You also know how to get from meters to micrometers. So 1 meter is equal to 10 to the 6th micrometers, so these are very small, or the opposite, which is 10 to the 6th micrometer, is equal to 1 meter. So now that we have our two equalities, we can go from centimeters to meters, as well as from meters to micrometers. Our second step is to create our knowns and unknowns. So we know that we have 0.073 centimeters, and what we don't know is how many micrometers that is. So let's create a plan. We have to start with what we are given, so we have centimeters, and according to our equalities, we can go to meters. We can't go directly to micrometers, unfortunately. And we also know that we can go from meters to micrometers according to our second equality. So let's put that into play. So start with what you know. Oops. So 0.073 centimeters over 1 times, now we need centimeters on the bottom. According to our 4 different equalities, only this one works. So 100 centimeters on the bottom, 1 meter on top, but when we cancel out those units, we're left with meters. That's not what our unknown is, so we have to keep going. Next, we would have to put meters on the bottom, and we need to get to micrometers. So this one wouldn't work because that's the wrong spot for our units. This one is a possibility, but that gets us to centimeters. We don't want that one. So we're left with our final equality, which is 1 meter equals 10 to the 6th micrometers. So whenever you multiply straight across and divide by your bottom values, you would get 7.3 times 10 to the 2nd micrometers. And as always, these are all drawn out for you in your PowerPoint, including all of the conversion factors that have been